All right, buckle up, everybody, because we are diving deep into some really cool astrophysics today. We're going to be tackling dark energy, and specifically this idea that, well, what if it's not so constant after all?
Yeah, that's a pretty big question. And we'll be using a really fascinating article from Quanta Magazine as our guide. It's all about an incredible instrument called the Dark Energy Spectroscopic Instrument,
Mm-hmm.
or DAI for short.
ASI, yeah. I was reading about this thing. It's like not just a telescope, right? It's mapping the entire cosmos.
It's really something else. It uses, get this, 5,000 robotic fibers. Each one can target a galaxy and analyze its light.
Wait, hold on. 5,000 robotic fibers. That just sounds like so sci-fi.
It's straight out of a movie, but it's real.
Yeah.
And the
Yeah.
reason that's such a big deal is the sheer scale of data it can collect. We're talking about mapping millions of galaxies in a fraction of the time it would have taken us before.
Oh, okay, I see. So it's like speed and precision all rolled into one, which is, I guess, essential when you're trying to understand something as mind-boggling as dark energy, right?
Exactly. And before we get too far, it's probably good to make sure everyone's on the same page about what dark energy actually is.
Yeah, because it's one of those things that sounds kind of, I don't know, like almost made up.
It does sound like science fiction, but this is real, and it's a huge deal. See, dark energy makes up like 70% of the universe, and it seems to be the force driving this accelerated expansion we've been observing.
Right, the expansion, yeah. For a long time, didn't people think the universe was slowing down? Like gravity would eventually pull everything back together?
That's what everyone assumed, based on what we knew about gravity. But then we made these observations, and boom, everything's flying apart faster and faster.
Almost like someone's constantly adding more space, more universe. It's really hard to wrap your head around. But how does DSI actually help us make sense of it? I kept hearing about this sound wave analogy.
Ah, yes, that's a good one. So DSI uses something called baryonic acoustic oscillations, or BAOs for short. Think of these as ripples from the Big Bang itself. They left a specific imprint on how galaxies are distributed.
Okay, so it's like leftover echoes of the Big Bang. But how do those help us measure dark energy?
It's all about using those ripples as a cosmic yardstick. By analyzing the spacing of galaxies and how that spacing has changed over billions of years, we can figure out how dark energy has shaped the universe.
Okay, I'm starting to follow. So we're using these ancient sound waves to track the expansion, and that tells us about dark energy. But that brings us back to our big question, right? What has DSI actually found? Is there evidence for this idea that dark energy is fading?
Well, the data is still being analyzed. But what we've seen so far, combining DSI's observations with other sources like the cosmic microwave background, it suggests something pretty remarkable. It looks like dark energy might not be constant after all. It might have actually been stronger in the past.
Whoa, wait a minute. You're saying the force driving the universe's expansion could be, like, losing steam?
That's one way to think about it. And if it's true, it would completely overturn our understanding of how the universe works.
This is huge. So we've got this crazy powerful instrument, DESI, mapping the cosmos like never before. And the early hints are that dark energy might be weakening. Where do we even go from here?
That's what we'll dive into in part 2. We'll look at the implications of this discovery and explore what it could mean for the future of the universe.
Okay, I'm definitely on the edge of my seat, so don't go anywhere. We're just getting started. Okay, so we're back, and I'm still kind of reeling from that last revelation. If dark energy is actually fading, what does that even mean for the universe? Like, what happens next?
It's a big question, right? We've built so much of our understanding on this idea of a constant dark energy. To think it might be changing, well, it throws a lot into question.
You mentioned earlier that DI's findings are backed up by other data too, like the cosmic microwave background, that sort of thing. How do those observations fit into the picture of this thawing dark energy?
Right, so it's not just DSI telling us this story. It's like we're getting these hints from all over. When we look at the cosmic microwave background, which is basically the afterglow of the Big Bang, it tells us about the early universe and the conditions back then. And those conditions, they just don't line up perfectly with the universe where dark energy has always been the same.
Okay, so it's like different pieces of evidence pointing to the same conclusion, but I'm still struggling to grasp what this actually means for the future. If dark energy gets weaker, does that mean the expansion slows down? Or could it even, like, reverse?
Those are definitely possibilities. If dark energy is what's driving the accelerated expansion we see now, then if it weakens, that expansion could slow down. Now, whether it would completely stop or even reverse, that's a much harder question. It depends on how much dark energy weakens and over what timescale.
Oh, right, of course. We're talking about cosmic timescales here, not exactly something we can just observe in a human lifetime.
Exactly. We're trying to predict what might happen billions of years from now. But even just the possibility of a slowing expansion, it's a huge shift in how we think about the universe's fate.
It really is. Earlier, you said something that kind of blew my mind about how this could challenge our fundamental understanding of physics. Can you unpack that a bit? What do you mean?
Sure, so a lot of our current physics theories are built on the assumption of, well, constancy, that the laws of physics are the same everywhere and every when.
Yeah, that makes sense, right? Like
Yeah.
gravity works the same way here as it does in a galaxy billions of light years away.
Exactly, and that assumption has served us well so far. But if dark energy is changing, it suggests that maybe some of those fundamental constants, those bedrock laws, might not be so constant after all.
Whoa, okay, that's heavy. So the very rules governing the universe might be in flux.
It's a radical idea, but it's one we have to consider.
Are there any theories out there that could explain how this could even be possible? You mentioned something about scalar fields earlier.
Yeah, scalar fields are one way physicists are trying to make sense of this. Think of it as an invisible energy field that permeates all of space. The energy level of this field, it can change over time. And as it changes, it could influence the strength of dark energy and therefore the expansion of the universe.
So the scalar field is like this hidden layer, subtly tweaking things behind the scenes.
That's one way to visualize it.
Are there any other explanations out there, like competing theories?
There are, and some of them get pretty wild. For example, some physicists propose that the universe might go through cycles of expansion and contraction.
Wait, cycles? So like expand for a while, then contract, then expand again?
Exactly, almost like a cosmic heartbeat.
That's mind-blowing.
It is, and it's still very much in the realm of speculation. But it just goes to show how much this discovery is shaking things up.
It's like every answer we get just leads to more questions.
That's the nature of scientific exploration, right? We're constantly pushing the boundaries of what we know.
So where do we go from here? What are the next steps in trying to unravel this dark energy puzzle?
Well, for one, DSI is continuing to collect data. The more information we have, the more we can refine our understanding. And on top of that, we've got new telescopes and observatories coming online soon. They'll be able to peer even deeper into space and time, hopefully giving us even more clues.
It feels like cosmology is about to enter a golden age. What are some of the biggest questions you're hoping to answer in the next few years?
So many. We still don't really know what dark energy is, what's it made of? How does it interact with the rest of the universe? And of course, the big one. What does this potential evolution tell us about the ultimate fate of the cosmos?
Big questions indeed. It's humbling, but also kind of exhilarating to realize how much we still don't know. We're right on the edge of some potentially revolutionary discoveries.
It's a truly exciting time to be a cosmologist.
Well, I, for one, am hooked. But before we get too carried away, I think we need a moment to process everything we've learned. So we'll make a quick break, and when we come back, we'll explore what all of this means for our place in the grand scheme of things. Welcome back to the Deep Dive, everyone. It's amazing to think about everything we've discussed so far. This idea that dark energy, something we thought was constant, might be changing. It's almost like discovering a whole new continent on a map we thought was complete.
Yeah, it really makes you question what else we might have gotten wrong.
Exactly. Like, if dark energy isn't what we thought it was, what other fundamental assumptions about the universe might we need to rethink?
Well, one of the big ones is gravity.
Gravity.
Our best theory of gravity, Einstein's theory of general relativity. It's been incredibly successful at explaining how the universe works on large scales.
Right, like how planets orbit stars and how galaxies move within clusters.
Exactly.
Yeah.
But general relativity is based on the assumption that dark energy is constant.
Oh, I see. So if dark energy is changing, then maybe our understanding of gravity needs an update too.
That's one possibility. It might be that general relativity still works really well in most situations, but that we need a more complete theory, something that can account for this evolving dark energy.
Okay, so maybe Einstein wasn't totally wrong, just incomplete.
Something like that.
But it's not just gravity, right? You were saying earlier that this could have implications for our understanding of, like, the fundamental building blocks of the universe. Like, what makes up matter and energy?
Exactly. Our current understanding of particle physics, something called the Standard Model, it's really good at explaining the particles and forces we know about.
Right, like electrons, protons, neutrons, all that stuff.
But the standard model doesn't really have a good explanation for dark energy.
So maybe there are new particles or new forces that we haven't discovered yet.
That's definitely a possibility, and those new particles or forces, they could be playing a role in how dark energy evolves.
This is getting pretty mind-bending.
It is, but it's also incredibly exciting.
I mean, it's a bit overwhelming to think about how much we still don't know, but at the same time, it's like we're on the verge of some truly groundbreaking discoveries.
I agree. It's a privilege to be a scientist at a time like this.
So what are the next steps? What are you and other scientists focused on right now?
Well, one of the biggest mysteries is the nature of dark energy itself.
Right, we've been talking about how it might be changing, but we still don't really know what it is.
Exactly. What is it made of? How does it interact with the rest of the universe? Those are some of the most fundamental questions we're trying to answer.
And how do we even go about answering those questions?
No, DSI is still collecting data, which is incredibly valuable.
The more data we have, the better our picture of how dark energy behaves.
Right, and we're also looking forward to new telescopes and observatories coming online.
Like the James Webb Space Telescope or the Vera Rubin Observatory.
Those will give us even more powerful tools to study the universe.
It really does feel like we're on the cusp of a golden age of cosmology.
I think so too.
You know, we've been talking about all this on a cosmic scale, but I wonder, does this discovery have any implications for our understanding of ourselves, our place in the universe?
That's a great question. I think it's a reminder that we're part of something much bigger than ourselves. The universe is this vast, mysterious place, and we're just beginning to understand it.
It's humbling.
It is, but it's also incredibly inspiring.
I agree. It makes you want to keep learning, keep exploring.
Exactly.
Well, on that note, I think we've come to the end of our deep dive into the world of dark energy.
It's been a fascinating journey.
Thank you so much for joining us and for sharing your insights.
It's been a pleasure.
And to all our listeners, thank you for tuning in. We hope you've enjoyed this exploration of the cosmos. Keep looking up at the stars, keep asking questions, and never stop exploring.